All right, ladies and gentlemen, welcome to the Burma Nation. This is my humble abode. This is our basement kitchen. It's also a workout zone. So today we're talking about Chapter 3, Lesson 1. It's called Graphing Linear Equations. There's some things that we need to be well aware of how to do to make today's lesson be successful for you. So we need to know that a linear equation is any equation that forms a line when it's graphed. We need to know that the word constant means just a number that's by itself, just a regular old-fashioned number. And we also need to know that standard form is a way that we can show linear equations. Standard form has its own little special stuff that we need to know. It's in the form of ax plus by is equal to c. A is just a number that is greater than 1, like it says right there. Should we highlight that so you guys can see it? And then b is just a number that's not going to be 0 as long as a is also not 0. C stands for constant. So a is again just the number in front of the x. It's the coefficient for x. B is the coefficient for y. A has to be a whole number that is greater than 1. So up in this problem, you see a 3x plus 2y equals 5. That's because A is 3, B is 2, and C is 5. In this equation, we have something different going down. All right, so everybody ready? Sweetness. All right. First part of our assignment is going to be able to have us asking the questions, are we able to determine if an equation is linear, basically just by looking at it. If it is, we'll put it into standard form. If it's not, we'll just say it's not linear. So on our very first example here, we have a 5x plus 3y is equal to a z plus 2. Now, the biggest issue with this specific problem is this z. There is not a z in ax plus by equals c, so this one's not linear. We might as well not even try to do anything with it because we just know it's not linear, and they told us to determine if the equation is linear. Example 2. We have, I'll go red this time. We have the equation of y equals a 4 minus a 5x. And because this has an x, a y, and a regular number, we know that this is something that we can put into our standard form. It is going to be a linear equation. So we just have to solve for, I guess, the x and the y to be by themselves. So what we're going to do is we're going to, in this case, because we have a negative 5x's, the smartest thing to do would be to add 5x's to both sides and get ourselves with a situation where we have x's and y's on one side and then our constant on the other side. So this is going to turn into a 5x plus 1y is equal to 4. Now you may be asking yourself this very simple question of, well, Mr. Berman, would it be wrong if I put it y plus 5x? The answer is yeah. That's not standard form. Just switch them around so that they're in the correct order. Now example 3, everyone's favorite stuff, fractions. Now fractions don't have to always be scary things for us, even though for some reason they are. Our job is to get rid of them. We have to have a number that is going to be a whole number to be our coefficient for the x, the a. So to get rid of fractions, we multiply by a common denominator. The common denominator in this case would be a 4. So each one of my problems is going to get multiplied by a 4. Now by problems I mean each number in the equation. So that makes this cancel out, because times 4 and divide by 4 just makes a 1. So we're left with 3x's for the first part. 4 times a negative y makes a negative 4y. And this 4 times an 8 makes a 32. So then this is in ax plus by equals c form. It's in our standard form, and we are happy. Example number 4, we have a second power. It is not linear. This would make one of those goofy looking parabolas. If I could spell, we'd all be happier. So let's keep it rolling. Sometimes they ask us to find things using the x and y intercepts. Now, we should all know that this is the y-axis, this is the x-axis, and that when we cross the y-axis, it comes with the ordered pair of 0, 1. So that is my y-intercept. And when we cross the x-axis, it's going to be something comma 0. That's my x-axis. So if you look over here at this horizontal line, it's where y is crossing at 2, and no matter where I'm at on the x, y is always at 2. So this makes a horizontal line, y equals 2. Now in this blue line, we have our vertical line where x is going to be 1. So no matter what the value is for y, x is always 1. And that's why it's just an x equals 1, because there's nothing else here to tell us it's going to be different. So what happens when we get those word problems? So here's where you might use something like this in the real world. In a box of peanuts, it's poured into a bag at the rate of 4 ounces per second. Nobody cares about this. The table shows that there's a function relating to the weight of the peanuts in the box and the time in seconds that the peanuts have been poured out of the box. Now, the only people who would worry about this are the people who are trying to get you to eat the peanuts faster. So they want them to come out as fast as possible. Now, it says to determine the x and y intercepts of the graph of the function. So we're going to plug the numbers that are up here on the chart onto the graph. So at 2,000, we're at 0. So right here is our 2,000. At 1,500, 125, 1,500 right here. And then at 250, we're at 1,000. Did I do that right? Yep, kind of. And then at 375, here we are at 500. That's right there. And then over here at 500, we're at 0. Now imagine that this is the y-axis, and this is my x-axis. So we're only looking at quadrant number 1 right now. We'll make this dot a little bit bigger. So what we have going on here, if this were to continue on, it would provide us with a little bit of information that we need to know. The x-intercept is always when our y is equal to 0. So we're going to have something for x, and y is going to be equal to 0. That's my x-intercept. So if we look over here at our numbers on the graph, our x-intercept happened when y was equal to 0. So if this is x, this is y. When y was 0, our x was 500. So here we are at 500, comma 0 for our x-intercept. And then our y-intercept is happening where x is equal to 0, which happened up here at 2,000. So x is 0, and my y is 2,000. So what does that stuff mean? Well, if you think about it, we're talking about a box with peanuts in it, and we're pouring things out. So way up here at this spot where my y-intercept is, that's how many peanuts there are in the box to start before we start pouring it out. So the y-intercept is where we began. The x-intercept is how much time it took for the box to be poured out and become empty. So that's something that we need to look at. So let's check out some more things. If we were to graph using the intercepts, you're going to graph this equation. We know that if we're finding the x-intercept, y equals 0. So what you do is you plug a 0 in for the y. So it says 4x minus 0 is equal to 4. Now we all know that 0 is nothing, so we don't need to worry about it with this problem. So we're going to divide by 4 to get x by itself, and x is equal to 1. Now if x is equal to 1 when y is 0, that's to the right 1, up 0. That makes the order pair of 1, 0. Now the next step would be to find the y-intercept. If we're using the y-intercept, x equals 0. So what we're going to do is we're going to say 4 times 0 into the original equation minus y is equal to 4. So solving this equation, 4 times 0 has always been 0. So we have a negative y is equal to 4. So we're going to divide by a negative 1 to make a positive y. That gets rid of our negatives. And then y is equal to a negative 4. So if we were to graph that, we come on over here, down 1, 2, 3, 4, put a dot, and then we can connect the dots and know that this is what our graph is going to look like. All right, folks, take a gander at this. Let's skip that one. Take a gander at this. We're going to do this as our first problem when we come into class. This is graphing by using a table. This is the Bermination. We're signing off. See you later.